this series of videos I'm attempting to repair and restore a PDP11-34 vintage computer. I'm currently working on some faults in the CPU, and it's proving to be a bit of a tricky one to get working. I keep getting new faults developing as I'm working on it, and this is very typical of a machine of this age, is that as it's run for or brought back to life after being idle for decades, we will get failures of various devices, and because of the nature of the way this CPU works, it can create all sorts of weird and wonderful effects. In the previous video we were looking at the test program I was running, which is this, and it was looking like we weren't properly remapping the addresses. Now, some suggested that possibly it was an interrupt being thrown because the serial card was not working correctly, or DMA issue. I don't have any DMA cards in this at the moment. I've checked the DMA lines. There is nothing being thrown that way. In fact, it's got nothing to do with the serial card. It's actually a fault within the CPU, or possibly the backplane. And the reason I say that is because, as we'll see in this video, it doesn't actually make any difference whether we are trying to read and write from and to the serial card or some other address. That's not what's going on here. So we'll look at that in more detail as we go through this video. The other thing to bear in mind when we're doing this is that when we use the console to read and write addresses and data, it's not using the same mechanism that the CPU uses. It's obviously a different connection to the Unibus. And also the way that the addresses are derived is very different on the console. So just because we can read and write something with a console doesn't mean that the CPU should be able to do it as well, because it might well be there's an addressing issue within the CPU. So what I was doing after the end of the last video was looking and trying to track down why the addressing of the card was wrong. That is, why will the program, the test program, work when it's referencing RAM and not when it's referencing the serial card? Hence the comment that it could be something to do with the serial card. It does, or did look like the serial card was at fault. Now, I knew that wasn't the case because of other testing that I'd done, but I can only cover so much in the video, so apologies if I'm kind of misleading you a little bit, but I'm just trying to take you through the process as I'm doing it. So what I was doing after the previous video was single-stepping instructions using the logic analyzer to see what was being put onto the Unibus. And remember that I have the logic analyzer connected to the Unibus at this point, and that is quite important to remember that. Because I've had problems with the backplane already, remember that just because the value on the Unibus is correct does not necessarily mean that the value going in and out of any of the cards plugged into a different slot in the Unibus is correct. In other words, the slot we're looking at might not be representative of every slot if there are poor connections on the backplane. But what I found was that the mapping, when we try to essentially read the status register on the serial card, which is what we're doing with this instruction at address 6, I was getting the correct address on the Unibus according to the logic analyzer. I was seeing an address of 777564, so the CPU was correctly remapping the data, the address lines. However, when we came down to this instruction at line 12, the value I was seeing on the Unibus was not what it should have been. It should have been 777566, which is this address plus the offset of 2 we have here. But what I was seeing was 037566. So I've printed this out just to hopefully make it a bit clearer, because that threw up some alarm bells. So what we should be getting is this top number, and this is for the TX transmit register on the serial card. We should have been seeing a value of 777566 octal on the Unibus, and that's this number in binary. However, what we were getting instead was 37566 octal on the Unibus. and that's this number. And if you look at this, you'll see that the biggest difference here is the top four digits are 0 when they should be 1. Now if you're familiar with this CPU, you'll know that although it's a 16-bit machine, it is designed to operate in 4-bit chunks, so it kind of breaks the 16-bit up into 4 chunks, and it kind of handles them separately. Even the ALU is in 4 separate parts. It's all in parallel, they all run side by side at the same time, but it breaks the 16 bits into chunks. And so if we look at the addressing portion of the schematic, then we have the address in out here that comes through the buffer chips, the bus drivers, but we then have this relocation set of multiplexers. Now if we look at this, we'll see that it's these top 4 bits and they all come through a single device, but I know it's not this device that's at fault, because when we try to put the address onto the Unibus to read the card, the address is correct, so we know the output is correct. It's only when we're trying to read it that it's had the wrong address on the Unibus. Now it's not quite as straightforward as it might sound, because again we know that this output here must be correct because it's common to both read and write, but when we go back further into the CPU, it's a fault that could be anywhere in the decoding of the instruction, and it just means that somewhere along the way we're kind of getting the wrong values. Now when I started investigating this, the signals coming out of this particular device were wrong. It didn't look quite right. Unfortunately, at that point the behavior of the CPU completely changed again and it started doing different things, so I think another fault's crept in. But this is not quite as straightforward as it might appear, in that the fault for just 4 bits missing could be much further back. And not only that, you have to bear in mind that what it's reading on the Unibus is an instruction or an address data, and if it's reading the wrong values in, then that's going to make it do the wrong thing. And so what we have to do here is, the next step to take, and that's what we're going to do next in this video, is that the data value I was seeing when we were reading the data, so that's when we were reading the address at 777564, that was being taken, what I was seeing on the logic analyzer was being taken from the Unibus. In other words, it was being taken on the outside of these input drivers. So these devices are an output section to drive data onto the Unibus, and then the input buffer takes the incoming data from the Unibus. And it's quite possible that it's actually reading the wrong value. Although we're seeing the correct value on the Unibus, it might be that the CPU is reading the wrong instruction value back from the Unibus. So it might be one of these input drivers is incorrect. And so what I'm going to do is I'm going to disconnect the data lines from the Unibus, leave all the other lines connected. I'm going to connect the data lines on the logic analyzer to the output of these bus driver chips. So we'll be looking at the data still, but we'll be looking at the data as seen by the CPU and not what's on the Unibus. I'm not talking here about the connections to the inputs, I'm talking here about the output of the bus drivers, so we'll see what's actually going into the CPU card and whether that matches what we expect to see. It's correct on the Unibus, but obviously somewhere along the line it's going wrong. Further to that, the reason I don't think it's a problem with the serial card, in fact I know the serial card has some faults, but that's not what we're chasing here. And we'll look at this as well in this video, is there is it's something that's specific to certain addresses or certain bits in the address. And we'll look at this in more detail later, but the program will run quite happily if we read and write RAM addresses instead of the serial card. However, it only works at particular RAM addresses. I'm not talking here about below a certain address and then above a certain address it doesn't work, indicating that maybe we're just trying to run off the end of the RAM. I'm talking here about it might work at an address like 1036, but it won't work at the address 1040. It'll then work at 2036, but not at address 2040. So there's a kind of a pattern here, and hopefully you're kind of seeing the direction I'm going with my thinking as to what we're going to try and chase here. So it could be there's just a bit on the input to the CPU that's not properly making it into the CPU, but that's what we want to look at next. No point going into the inner workings of the CPU until we know that the data going into it is correct. So that's what we're going to look at. I'll get the logic analyzer hooked up. Again, it'll get quite noisy. I'll have to have the fan running, and the logic analyzer is quite noisy as well. But I'll get the logic analyzer hooked up, so it will be hooked up very similar to how it was previously. The only difference will be the data lines will be on the input side of the CPU bus drivers rather than on the unibus itself. I've got the program re-entered. The difference now is I have the logic analyzer connected the same way it was. It's mostly connected to the unibus, except I have the data inputs connected directly to the CPU card. So if we look at one of the sheets in the schematic, there are 4 of these. As I said, the CPU breaks the entire 16-bit data path up into chunks of 4 bits. And so what we're looking at here is, it's not the input from the unibus, we're actually looking at the outputs of the input buffer. And so there are 4 chips, as I said, it's spread across 4 chunks of 4 bits. 4 bits per chip, and these are the bus drivers that I mentioned. But we're looking at the output of the bus driver, not the input to it. And so what I'll do is I'll move the camera so that you can see the logic analyzer. We'll try and run the test program and see what results we get. So I've got the logic analyzer set up to trigger on address 1002, and looking at our test program, it should trigger when we hit the second line of our test program. So I'm going to arm the analyzer. Now I'm going to try and run the test program from the start address of 1000. So you can see it did something, but it's halted. The CPU is halted as it normally does. So although the analyzer has captured something, what I'm going to do now is I'm going to single step the program through a few more cycles just so we can capture a bit more data. Okay. And I'm now going to stop the analyzer, and it should show us what it's captured so far. And so you can see it did successfully stop or start capturing rather at address 1002, and what we can now do is scroll through and see what it did. So at 1002, the data value it should have read, if we look at the test program, is, hopefully you can see this, so it's not very clear here, it's quite difficult filming over the top of the PDP, but the value should be 12701, and as you can see on the analyzer, that's exactly what it is, and that should be immediately followed by a read of data value 177564. So it's 2 words it reads for this particular instruction, and indeed at address 1004 the value is 177564, so that's correct. If we scroll across, then the next value it should read at 1006 should be 105711, which it is. That instruction is going to cause it to read the status register of the serial card at address 777564. So we should see on the bus the address 777564, which we are seeing. So we know it read the addressing correctly, otherwise it would be doing the wrong thing. Not only that, but we can see it successfully read the value of 200 octal from the serial card. That's just saying that the TX register is available. So that's correct. Remember, this is on the input side of the bus driver chips. The next address at 1010 or 1010 should be 100.376, which it is, and at 1012 we should read 11.0061 followed by a value of 2. So firstly 11.0061 and then a value of 2. And if we keep scrolling across, this is where things go wrong. What that instruction should do is cause the R0 register to be copied to the address 777566. And this is what I mentioned earlier. You can see that what's actually happening here is instead of 777566, we're getting 37566. In other words, the top 4 bits are stuck low again. It stopped doing this yesterday. I think it's a temperature thing. I think there's something that's borderline where there's another fault that's creeping in once the CPU warms up, and I've only just switched it on. So I think it's still cold enough to be going back to our original fault. But as we can see here, what we're getting now is the top 4 bits are wrong. So it's writing to the wrong address. But what's kind of strange is it shouldn't really matter. That address 37566 is in the available RAM. So even if it writes to that address, it shouldn't matter. It should just carry on writing. It doesn't really care or even know necessarily that it's not writing to the serial card, but it should not halt the program. We should keep going. So although everything is correct, it's halting at this point. So something internal is not working in the CPU, and it's causing what should be a valid write to a valid address that shouldn't cause the processor to halt. It's actually causing the processor to come to a standstill. So that's what I need to start investigating next. And what I'll do now is I'm going to change the address. If you remember in the previous video, the address 177564 was to point us to the serial card. I'm going to change that address to 1036, and we'll try and rerun this and see what happens. So I'm just going to change the program. Okay, I've got the address set to 1036, so that's our target read address. The target write address is too high than that, and just to keep the program happy, I'm going to put the value 200 octal into address 1036, and then I'm going to clear the address above that. Okay, so now I'll reset the analyzer and we'll trigger again and see if the program will actually run. And as you can see, this time it's carried on running. All I've done is change the address, and if we now start scrolling through, you can see we're getting exactly the same results, except when we get to this address, the next address is where it's going to try and write. We are indeed writing to the correct address. So we've got the next address, or it's the address +2 above 1036. And the first time round it's writing 1000, and if we keep scrolling across we loop round. And next time round you can see the value that's been written is 1. So it is successfully incrementing the R0 register. It's copying the correct data. So it's all working fine. And what I find is, depending on the address that I set, it will work, and then at certain addresses in RAM it won't work, and it's fairly random. What I do find is that if I then look at multiples of that address, so if I add 1000 octal to the address, for example, for the working addresses, it continues to work, and then other addresses it won't work, and again if I go to multiples it stops working again. So you can see that there's something very strange going on. It's now still running. So this is the process I'm going through, working my way further and deeper into the CPU, but I'm doing it incrementally. I'm not kind of jumping straight into the ALU or the address decoder, that sort of thing. I'm trying to figure out exactly where this is going wrong. We know that although the address coming out is incorrect, it's not the bus driver, because the address earlier for reading that high address is correct. The relocation is working, because again that read, it's only 2 addresses lower, so it's not that that's causing it. It does appear to be able to read the instructions, at least in through the bus drivers successfully. Whether it's them processing that data correctly is another matter. It seems to be for most of the bits, otherwise it wouldn't run at all, even at the lower address that we're using in RAM. The fact it sometimes does the same thing at certain RAM addresses tends to indicate that we've got an issue somewhere with one or more of the 4-bit blocks is not being properly processed, and it's now a case of working my way back through the CPU to find out why that address is coming out incorrect. It's correct when it reads, but it's incorrect when it tries to write. So that's what I'll be looking at the multiplexers, the address decoding, finding out the difference between the read and write address source, and trying to figure out why those top 4 bits are not what they should be. Okay, so that's it for this video. If you're getting bored with this process, then let me know. I don't normally show this sort of thing because it is quite tedious, and it does make the repairs look like they take a long time, and that's because they do. It's just that mostly I skip through all this, and it doesn't take as long as you might think. It takes a long time trying to explain it and talk through it, but normally I go through this process quite quickly, so trying to film it and post the videos slows it down. But hopefully it makes it interesting for some people, so hoping that this is of some interest to someone out there.